what I tried to do before the break was like give you a flavor of these probabilistic logic programs, also a little bit of what you can use them for, and then continue on like how you do inference, because inference is like the key problem. What I'm going to do next is like continue a little bit on the inference. I'm going to also make the connection with what Vaishak was talking about yesterday, which is this weighted model counting. Give you a little bit of algorithms, and towards the end maybe also show like the challenge, which is lifted weighted model counting, if that works out. And in the middle, I'm going to skip the learning part. That's for Fabrizio tomorrow. And then I'm going to also show you some of the applications in detail, especially the dynamics I'm going to talk about. I'm also going to talk about our newer work, which is on mixing Problog with deep learning in a very easy way. So that's like what is left for now. And you'll see that the enabling technique for the deep learning is something extremely powerful. It's working with semirings, and it's what's called algebraic Problog, A-Problog. Because working with a probabilistic semiring is just one possibility, but you can see, and that's going to be the first part, that really working with algebras and semirings give you so much power that you can do loads of other things like computing gradients, like working with other things, and that's quite neat, I think. It's a little bit technical, but I mean the gist of this talk is that you get some of the ideas, and of course if you are interested, well, I'll be along well a lot of the week of the rest of the week, and of course there's also pointers to some of the papers and some of the works that you could have a look at, and I'm happy to discuss afterwards. There was also like an interesting question that came up during the break, which is like, okay, what is now different with regard to traditional graphical models or Bayesian networks or dynamic Bayesian networks? And I guess the key thing that you have to keep in mind here is that you get two things extra. The first thing is, this is a programming language, right? So whatever you can write in a programming language, you can write here. But you can do more. I mean, probabilistic programming is all about like injecting probabilistic primitives in these languages, and that allows you not only to reason probabilistically, but it also essentially allows you to learn, because learning is nothing else than Bayesian inference, and you can actually train these probabilistic programs using data. I mean, you can learn the parameters in the case of these logics. You can often also learn the structure or part of the structure by training. So that's one thing to keep in mind. You get a lot more expressive power here. The other thing that you get is logic. And I mean, there's a lot to do in the AI field about type 1, type 2, about low-level, high-level reasoning. I mean, the Kahneman thing is like, okay, type 1, type 2 reasoning, the kind of reactive reasoning or the kind of deeper reasoning for which you really need a chain of deductions. And I guess I would argue that logic gives you, in any case, the high-level reasoning abilities. I think also probabilistic reasoning is something that is very powerful. It gives you explanations. The neural networks, and we'll come to that a little bit later, they give you the low-level stuff. I think, but for reasoning, I think so far they are, in my opinion, I should be careful here because I'm on record to say. But in my opinion, they're still very limited in terms of reasoning power. And so I guess one of the key challenges is really how you can combine all of that. But I guess both probability, logic are very good at high-level reasoning. By the way, there is an excellent YouTube video by Adnan Darwish, who really also argues about all this kind of the need for logic and for reasoning. So I think that's the other thing that it buys you. And of course, you get a lot more expressive power. I mean, the fact that you can merge something like graphical models with logic is kind of interesting, because it would also allow you to incorporate, for instance, ontologies into Problog almost directly. It supports that kind of reasoning, and so it gives you a mixture of the two. And of course, this is not the only framework. There are others. You'll hear about other implementations and other visions tomorrow. Also, Markov logic is kind of a well-known framework in this regard. But I guess that's like the reasons for doing this basically. Any other questions about this at this stage? Okay, if not, then let me briefly come back to what I've said about inference. Okay, I've said you combine always like the logic reasoning part with the probabilistic reasoning part. And in a first step, if you're working with these probabilistic logics or first order logics or probabilistic first order logics, what you always do is like you reduce that kind of reasoning to some kind of propositional logic, except in the case when you're working lifted, but you're always reducing it to a form on which you can do the probabilistic inference or the kind of counting inference. You're always doing that. And in logic, there are two ways of doing that. I spend a lot of time in showing that if you do Prolog, well, you can just prove, right? Prolog is something that builds refutation proofs that why goals are true. There's another thing that you can do, and that's like the model theoretic way. That is what answer set programming is all about. Basically, what you do in this case is what I tried to illustrate briefly on this slide. What you have here is again like a little Problog theory, and rather than proving why Carl is stressed, what you do is you ground out your theory for smoking, so that it contains all the relevant rules that can be used to prove that Carl smokes. And then you get very much like a kind of set formula. You get a logic formula, and you're going to very much do the kind of thing that you do in satisfiability. It just, and that's the key difference between satisfiability between logical reasoning, constraint solving, and probabilistic reasoning. If you do set solving, if you do constraint solving, you're interested in one solution. If you do probabilistic reasoning, you need to count how many solutions there are, because it's these counts that give you the probabilities ultimately. And so that is what's going on here. Very much like in plain logic, you can prove, and then you get logical formulas like these explanations that you can disjoin, and you can map them onto these circuits on which you can do the efficient inference. The other thing you can do is you can ground out, and that's very much the answer set programming style. You can ground out your series. This is very much what Markov logic is doing. You ground out, and you get formulas like this, on which you can then do the weighted model counting, and for which there do exist weighted model counters. So let's see as to how that works. I mean, here it's grounded out. You get these relevant rules for proving that Carl smokes, and you get a propositional theory. And then there is like this kind of logic programming style thing that I don't want to spend much time on, because it's getting very technical for those that are not into Prolog and these kind of things. But what you do get is, like, if you look at the rules, after grounding, there is only one left for Carl, right? Carl smokes if influence Bob Carl and smokes Bob, basically. Now, given that that's the only way that you can prove Carl smokes, people sometimes make this Clark's completion and just say, well, it works in both directions, and they reduce it to Carl smokes if and only if, whereas the original rule only said if, basically. For Bob, there are two rules, and so the Clark's completion would say Bob smokes if the first rule holds, stress Bob, or the second rule holds, which is influences and Bob smokes and, basically. And you get like another rule. And at that point, you get like a propositional logic theory on which you can do weighted model counting. And you can count how many models there are, basically, and that's the essence of probabilistic reasoning. Any questions about that? Oops. The screen seems blocked. Can anybody? Oh, okay. Okay, it worked. Sorry. A little technical problem. Okay, so now what I'm gonna do is I'm gonna continue a little bit on this difference between SAT, counting SAT, and weighted model counting. And I'm gonna go for the very basic DPL algorithm that allows you to compute, if you've got a Boolean logical theory, whether it is satisfiable or not. And I'm gonna expand that towards these other kind of problems like count sets and also weighted model counting, basically, because that's what we use in the probabilistic logics. The other thing that this is going to give me is like the ID, because all these algorithms are extremely similar. One algorithm is an extension of the other, and the thing that makes a difference is the semi-ring that you're using. You're using different operations, your different notions of plus and multiply. And by varying this, you get an extremely powerful tool to do all kinds of cool stuff, including gradients and deep learning, as I will argue later. So if you look at inference in Bayesian networks, and again, if people are not yet familiar too much with Bayesian networks, maybe it is not too important, but basically here you see a Bayesian network, and if you want to find a probability like this one, well, what you would do is you would take the joint and you would marginalize over all the variables that you're not interested in. And if you do the marginalization, then, well, that's basically coming to a sum like this. You can read off the factorization. I guess Christian introduced Bayesian network yesterday, so that is probably familiar. You get a factorization here. And then what people are doing is like they're pushing the sums inside, basically. They're basically pushing the sums inside, and you get a kind of sum product that is basically happening here. We take sums and we take products, and sums and products are like what you do in semi-rings. And so what all the algebra and all the variations are going to be about is like taking an alternative for the sum that we know and for the product that we know. For instance, I can take, instead of a sum, I can take a disjunction, and instead of a product, I can take just an and, a conjunction. And then I got a different semi-ring. And very much the same kind of things that apply here, I can make apply for these other semi-rings, with some caveats and some restrictions, and sometimes things get a bit more complicated. And that's the thing to keep in mind. So here you see like a SAT formula. In SAT, we're interested, given this formula, and we're interested in the fact, does there exist a satisfying assignment for that formula? And again, okay, one way of doing that, if you map it onto the Bayesian network formula, is like to take a disjunction over all these possible assignments, right? I can take A, B, and C to be both true and false. I can take these things, and then this is like what is one clause, basically, right? This is just what is called a clause, right? A disjunction is a clause. And then I've got a conjunction of clauses. And so what I have here is basically an OR of ANDs. It's kind of conjunctive normal form. And I got also kind of some product to compute here, basically. I can write it actually in this way, right? In going from here, I just taken this and I replaced that by a sum, and I'll replace that by a product, and I basically get it into the sum product form. And you see that what happens in Bayesian networks is actually also applicable to this here, basically. Yeah, so what I have here is I'm just interested in like finding this, whether there exists a satisfying assignment. I know if at least it's true once, then OR of 1 and OR of 1 and OR of 1 is always going to give me a 1. But I can, instead of taking the OR, and that's what I get in count OR, is I can actually take the sum, right? If I take a real sum, so that 1 plus 1 is 2 instead of 1 plus 1, I mean, if I work in the Boolean ring, 1 plus 1 is 1 in a sense. But if I take 1 plus 1 equal to 2, I can actually count how many models there are by just applying this kind of formula. And that will give me the number of satisfying assignments. And it's this which leads to weighted model counting, because here every model has weight 1, right? And so what I will do in weighted model counting is I will take the product over all the literals, basically. And I think Vaishak yesterday talked about how to do that. I mean, if you look at the product that we have here, then you get these weighted literals. And if you look at the first definition that we had for Problog with this distribution semantics, you see that we could have positive facts and negative facts. Now, if you take for the positive facts the probability P, and for the negative facts the probability 1 minus P, you'll see that here you'll get essentially the formula that was computing the marginal probability of a query in Problog. So that shows really that Problog can be reduced quite easily to this weighted model counting kind of setting. This is what you have here, and that's illustrated again on this slide. So we're interested in computing some products. Are we going to play with our semi-ring? So we're going to play with the plus, and we're going to play with the multiplication. There is typical kind of requirements of semi-rings. You can look them up in Wikipedia if you want, but typically these things are commutative, associative, and it is the fact that multiplication distributes over summation. I mean, we're kind of used to that in most algebraic structures. And then there is also an identity element for plus, which we will denote by 0. And there is kind of annihilating elements or an identity element for multiply, which we're also going to use basically. And so what we have is there are the variables. We've got the factors. The factors could be like the factors in a Bayesian network, but they could also be the clauses in the CNF form that we were working with. If we're working with Bayesian networks, okay, we got the normal, plus, and multiply. If we're working with the set, we get disjunction, conjunction. If we work with number sets, we get normal summation, and then, well, normal multiplication in a sense. So there exists a lot of algorithms for doing that. One thing that I'm going to show is kind of the standard vanilla algorithm that you can use, and that's the TPLL, Davis, Putnam, Loveland, and Logan. So it's a pretty famous algorithm in computer science, and it starts from these variables, and you start from a set of factors. And the way that it works is that if the set of factors is empty, then you return 1. That's like this annihilating element. If one of the factors can be evaluated, you evaluate it and you multiply and you say, well, let's take the rest of the factors that we still need. Otherwise, you select one of the variables and you assign it the value true or false, and you call things recursively. I mean, these algorithms are a little bit tricky to look at, so it's a lot better to look at them on a little example, which I will soon do. But the first thing, if we can evaluate a factor, and let's just look at the kind of Boolean case, the logical case, then, well, you can evaluate a factor whenever the empty rule, I mean, the empty disjunction is always false. And so that's the condition under which I can evaluate that. And I can add some further conditions. And now I'm still looking at the kind of SAT case. So my variables are propositions. These are the clauses, right? If there if all clauses have been satisfied, I return 1. If the empty clause, that's unsatisfiable, I return false. And otherwise, I call the procedure recursively. I take one of the variables, I assign it true. Take one of the variables, I take the same variable, I assign it false, and I kind of recursively call it. And these are like 2 optimizations that you can do. Again, in the case of SAT, if you have a literal that occurs in your factors, but the negative one doesn't occur. Well, in that case, you do know that it doesn't matter whether I assign that literal true or false, it will always be satisfied. So that's the case that is treated here. The other case is if there is a factor that says, okay, A, for instance, if the factor says A, I know A is a clause, it's in there, so A must be true. And then I will basically assign that value to the rule. It's pretty complicated if you look at it like that, but if you look at an example, things are a lot easier. This is the formula for which I want to find a satisfying assignment. You see it's written as these factors. The factors are clauses, X or W, Y or Z. I've got these 4 variables, and it's written as it's kind of written as a conjunction or a multiplication, basically. If I take that formula, well, it is not the case that the empty set occurs in there. It is not the case that there is a single literal. And so what I can do at that stage is I can take one of the variables and assign it one of the values. For the left, I take W equals to 0. The right, I take W equal to 1. And so if I take W equal to 0, well, I do know X or false, well, that is equal to X. And so my formula simplifies. I'll look at that part here. If I take W equal to true, well, I do know that the first factor, the first clause is satisfied. So all I need is that one. And then I kind of recursively build on top of that. Here I can take X, and the left branch is always taking X equal to 0 or to false. If I set X equal to false, I get the empty clause, and that will be unsatisfiable. If I set X equals to true, basically I know that the first condition will be satisfied, and I go to the right, and I still have to do this one. And you see that recursively I can build this kind of search tree, and at the bottom of the tree, at the leaves of the tree, I can see whether it contains the empty clause, like here. That is unsatisfiable. The disjunction that is empty is not satisfiable because at least one of the things must be true. Here I've got the empty conjunction. That's always satisfied. So here I basically have found a solution. One satisfying assignment is W equals to 0, X equals to 1. Here we've got Y equals to false, and Z equals to 1. That is a satisfying assignment, basically. And so that's like just the plain SAT case. I can now play with the game. I can look at the number of satisfying assignments that I need. And the elegant thing about this DPLL algorithm, and that's the elegant thing about working with semi-rings, is you've seen that on one of the earlier slides, what I did is I just replaced this OR by a sum. And in my algorithm, I only need to use the different sum. I mean, this will be the real sum. If this is 1 and this is 1, I'm going to return 2 now. And the other thing that I need to do is if I need to keep track of the number of factors, because I'm really counting models. But otherwise, the algorithm is very, very similar. If we look at exactly the same case, we do know that if we proceed, I mean, we're counting now how many models this theory has. If we're in the left branch, what you'll see, okay, well, that is not a model, so nothing below that will be a model. That still holds. I've got still this one. On this path, all of my variables have been assigned a value. And so that means, okay, I just have one model here because all my variables of interest, x, w, y, z, they all have been assigned a value. And so I got just one model for that. Here, it's a bit more interesting because here, well, I stopped because I know, okay, everything below will be a model, but I haven't assigned a value to z. Now, there's two possible values that I can assign, and basically, I don't care which it is, but if I'm counting how many possible assignments there are, well, if I would expand it, I would have one here, I would have had one there, and so I would need to take into account two, basically. And I can do the same thing here. I mean, this is at the same level. 3 variables have an assignment, so I got 2. Here, it's only 2 variables that have an assignment. And so there's 4 possibilities. Any other choice than W and Y, I mean, it doesn't matter what value I choose for X. It doesn't matter what value I choose for Z. It's going to be the solution. And so the total number of models for which this is formula is satisfied is just the sum of these, which should be 9, basically. And now we're almost at probabilistic modeling. I mean, what number set does is counts how many models there are, but what you're typically interested in probabilistic model is probabilistic modeling. You've seen that already at the start with the probabilistic prologue. In this generative model, all of my possible walls had a different weight, right? And that was because the probabilities play a role. And so what I do here is, and that's also what you see in the formula of Problog, the true facts get a weight, and the false facts get another weight. And the sum of the weights is equal to 1, right? Because probability of being false is 1 minus the probability of being true. And so what you need to do now is basically use that kind of formula. And of course, also, if you call recursively, you have to take into account the probabilities of these events. And yeah, you can do very much, you can very easily adapt that scheme to take into account the weighted model counting problem. And in the weighted model counting, every of your literals gets a weight. The negation of every literal gets another weight. If you're working with probabilities, the sum of the weights is 1. If you're not working with probabilities, like what you sometimes do in Markov logic or in other things, then the sum might be different. And then you still have to do something else. But you see here that, again, very much the same kind of algorithm just applies. And all what I've been doing is playing with different versions of multiply, of plus, and with my operations, basically. That's all I've been doing. It's different semi-rings that I've been using, and it's the same algorithm, essentially. If you take this algorithm and you can turn it into one that works for all of them by just changing the semi-ring. And that's like a key message that is kind of interesting. That's the weighted model counting again, and that's the approach that underlies a lot of probabilistic reasoning. I mean, to complete the grounding approach in the current product implementation, this is the way it works. You ground out, you reduce it to weighted model counting, and you send it to some kind of solver that will do weighted model counting for you, basically. And that solver will often, not always, be based on knowledge compilation. There's also techniques that will do sampling approaches, like in Markov logic, this has been popular. Also in the functional probabilistic programming, they only use like sampling approaches or largely use sampling approaches. And yeah, that's basically things. Let me check how much time we have. Okay. So given that exact computation of these probabilities and these weighted model counts and all of that is so hard, it's not surprising that people have to spend a lot of time on developing approximate inference techniques, and zillions of these apply. I mean, they are standard in graphical models. They're also standard in probabilistic programming, where things like MCMC, Hamiltonian Monte Carlo, a lot of likelihood weighting, rejection sampling, all of that is kind of being used. I'm not going to go into details about that. I've got also very few slides about that, but basically the standard paradigms do apply, and people are really, really interested in this kind of things. What I'm going to do now is look at some of the further parts, because I don't want to skip this. I'm also going to skip the learning part for Problog, because I count on Fabrizio to talk about that tomorrow. So let's look at some of the applications. And first of all, there is the dynamics. I've seen that Vaishak yesterday already briefly talked about that. But then the dynamics is what you need to tackle this kind of predictions, this modeling in multiplayer online games. It's also what you would do in a kind of relational reinforcement learning setting, which is just the adaptation of reinforcement learning to these relational settings. And what you're interested then is like building a model that would allow you to make predictions about the future given the current state. And if you're able to do that, you can also combine that with ideas for reinforcement learning to say which actions you should take in a sense. So you can all combine these ideas of well, you can basically build the kind of Markov decision process with these algorithms. And the key insight to model this, and again, look at the distinction I make is between modeling and solving. I mean, modeling is easy here. Solving is, again, a lot harder. But to model time in these systems, it's pretty easy. In a sense, what you do is, like you distinguish, like in the weather example, today from tomorrow, and you adapt your rules in such a way that, well, they're going to condition on the current state, and they're going to say something about tomorrow or about further points in time. So what this rule says is that, okay, if a city is owned by an owner and another city is close to that first city, and that is owned by an attacker, then at the next point in time, it could well be that that city is conquered by this attacker with a particular kind of probability. And so you very much get the kind of rules that I was referring to earlier on, like the ones that I was using to model the Earth, except that now, okay, this is for today, and this would be saying something about tomorrow or the future, the next point in time, basically. This is the kind of rules that you can basically use to do this. We've learned simple models with that for multiplayer online games, and we've been able to well, predict with reasonable accuracy a couple of steps ahead. Also, in the case of modeling how social networks would evolve, like who would next talk to one another, you can use this kind of model in like small chats. You can do that kind of thing. I think you've also seen these, but you haven't seen the movies. You can use the same kind of thing to model dynamics, and we've used that in simple robotic settings and simple tracking settings. And that's with the distributional clauses, where you have the continuous distributions that I was introducing. Let me just show that example. This is a scenario with magnets. you've got three types of objects: magnetic, ferromagnetic, and non-magnetic objects. And you do know that there are properties of these. You know that non-magnetic objects, they don't interact if they come close to one another. You know that if there are two magnetic forces, they either will attract each other or kind of repulse. And if it's a magnet and a ferromagnetic object, they will attract one another. Unless these objects are, of course, held. And so what we did was like in a little kind of demo. Let me see whether I can stop it. Where we're also like showing this to kids. And the fact is you're given three objects, and by manipulating them, you have to, well, determine which type the objects are really. And so we modeled that in DC by encoding the kind of rules that I might show on the next slide. And you see that initially, I mean, I've got three objects listed here, and they're equally likely to belong to one of these classes. Now the interactions, they will give me information about the nature of the object. And so you'll see that after interacting between two objects, you'll see that these distributions are gonna change basically. So let's see how that goes. You see that now the red and the blue interact, and there's no attraction, no repulsion, and so you see that the distributions here are actually changing. You then see another interaction, and you see that again the two involved distributions are changing. And now the cool thing is that by one further interaction, well, you can actually really logical reasoning, and you'll know the perfect class as a whole, basically. And that's an example of the real combination of logical reasoning. By all pairwise interactions, you actually determine with almost certainty the property of all the objects. This is a pretty hard task for kids to do, so they were quite impressed by this. I mean, it's not so impressive in terms of interface, but the reasoning is kind of illustrative of what you can do with a probabilistic logic. So let's continue with that. I mean, this is just the way it's represented. It's nothing else that I haven't said before. And we do use this particle filter inside, which is a standard technique to do inference in dynamic models. Just that it's made relational, and it's made also to cope with the logic, and there's some interesting things to be said about that, but it's pretty technical. So let's look at what we can do else with this. These were some things in a robotics project, and we're still continuing that line of research. Here, ultimately, what you want is tracked robots to do simple things after a couple of demonstrations. And this is a really relational setting. It is relational in the sense that there's multiple objects on there, variable number of objects, and the ultimate that you want to do here is with no or virtually no knowledge about what are the objects, also what are the effects of the actions, can you come up with a kind of planner that will well, configure the objects in a kind of desired way on a shelf or on a table. And so there were various stages of this research, and it's in a sense still ongoing. And in the first stage, what we were trying to do is basically, if you have distributional clauses, you could basically build a planner that will actually tell you what are the right actions to obtain a desirable goal state. For instance, if you wanna if you wanna move certain objects inside, then maybe you have to do a little sequence of actions, like you first make space on the table to be able to insert your object on the right place. And so it will actually detect that. Given that you have action knowledge about what will happen to the objects in the form of distributional clauses, which is a fairly complicated representation because you mix planning operations with continuous variables, right? The positions of these objects, and also with uncertainty about these positions. So it's a pretty complex setting for planning for AI. Given that you have these distributional clauses, you can actually build a planner that will do that. The other thing that you can do is from a sequence of kind of operations on these objects, you can actually learn the kind of rules for distributional clauses. Basically, what does it look like? Basically, you get like, this is a kind of exploratory so-called babbling stage where the robot tries out multiple actions and sees what the effects are on very simple configurations. Like here with just two objects. And you've seen that there was the ICAP robot. It was just a movie, the simulation. But we've also done it on the real robots, both with the ICAP and with other ones, where you can actually tap objects here, and then you see before the action, I have certain information about, say, the distance the positions and the distance between the two objects, and then I do a tap on, say, this guy with a particular force, and I see what the effect in terms of displacement is going to be. Given this kind of monitoring, you do have before action, after states, and from these you can learn the distributional clauses. The way that this works is you build a kind of decision tree-like thing in which you have these relational features, you incorporate the actions, and at the bottom you say something about the distribution that you should have in the head of the rule, basically. And we've done that also with this kind of Kinova arm and done some kind of planning. Of course, this is also still early days. I mean, this is like a limited number of objects. It's a limited setting, but it shows that, I mean, if one can scale this up, that would be a pretty useful thing to do because, well, you could scale it up to like kitchen scenarios, but that's still far away for a number of reasons. Basically, the inference and also the learning is too complicated. People have done other things with this. People that are interested and familiar with this kind of event calculus, they do know that event calculus, which is also kind of related to actions and activities and planning, can very straightforwardly be represented in logic programs, and you can reason with that. Now there have been people that have looked at these event calculi, people in Greece, and they've actually turned that, instead of using Prolog, which is deterministic, they've used Problog, and they were able to do kind of cool things in terms of action recognition and finding like the most likely action through observation. And basically what you get is like you observe videos, and there are certain low-level activities that are in there. This is like the elementary actions. Then you want to recognize some higher-level concepts, and they've done that with this kind of Problog reasoning. Okay, so let's look at the advanced stuff and slowly coming to the deep Problog, the connection with deep learning. I was saying in the DPL algorithm that you could play with semirings. If I choose other operations than OR and 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 turn them in generally like sum and product, I can do cool things. Now I did this just at the level of propositional logic. There's no reason why I should stick to propositional logic. And it was indeed like a very bright idea by Jason Eisner at Harvard in the context of computational linguistics, who made the system called DYNA, which is also a kind of, well, it's a kind of prolog, data log system that works with semirings, and that has been used in natural language processing. Now, what DYNA does is, instead of using and or in prolog, he uses plus and multiply, as in semirings, and he allows to write down very much the same kind of rules. And this is the kind of rules that you would need to write down a kind of kind of context-free grammar, basically, to encode. There is, for context-free grammars, there is the famous CKY or CYK algorithm that parses things in polynomial time, in cubic time, basically. And this is like a way of encoding it in DYNA. And the way that it works is, what you get here is you can rewrite a non-terminal into a word. And then if there is a word at that position, you will say that the non-terminal is at that position in your CKY algorithm. So CKY is like a dynamic programming approach to parsing. It feels like kind of matrix, square matrix. This is like the recursive rule. If X rewrites into Y and Z, you can find a Y from I to J, and you can find this Z from J to K, basically. If you don't understand really the details of this program, don't bother. In Prolog, you would just write implication here and conjunction there, and you would get a parser. What he does is get a probabilistic parser that uses here a sum. He will sum over all possible derivations. I mean, this is what you want. And if the derivations have particular probabilities, here you will basically multiply. So here he sums out. I mean, you see I've got X, Y, J here. And here he sums over all possible W for which this kind of conjunction or this kind of multiplication works. So this is like a sum product. This is also a sum product. It's just that here there is variables y, z, and j that occur on the right-hand side, but that do not occur on that side. And so this is what is called weighted logic programs. And I can give some other examples that might illustrate the point of this DYNA a little bit better. Here is a graph, right? This is a graph, and it's a directed graph. And say you want to check whether a node is reachable. Suppose you start at A, and then you want to look at which of the nodes are reachable. Using Prolog, you get this kind of recursion, so you could naively represent this in data log in Prolog. Well, something is reachable if I was initially there. That's what this one says. So A, if I'm initially in A, then A is reachable. And then I could say, okay, something is reachable, Q is reachable if P is reachable, and there is a connection from P to Q. So if I know A is reachable, and there is a connection from A to D, then I know that D is reachable, right? And so this is just like encoding this kind of simple past program. This is just Prolog. It's purely deterministic. It will tell you for all the nodes, is it reachable or not? Now, the interesting thing is that you can again use this sum product idea, and the sum product ID is illustrated here, right? I can say, like, suppose that I traverse one of these edges. In order to traverse it, I need to pay a particular cost. There's maybe a distance between the two nodes, and you can encode that here. Initially, well, that doesn't have a cost, but all the edges have an associated cost, basically. And then the thing to do is, well, you take the plus, you replace it by a minimize. I'm going to minimize over all the possible here, right? On the left-hand side, I've got Q. On the right-hand side, I've got P and Q. But that means I'm going to eliminate P here. I'm going to take the minimum over all P of the edges that lead into Q, basically, right? So for instance, yeah, if I take D, then, okay, it's going to be reachable by taking 20, right? Suppose I know it's reachable, and my value for reachable is 20. Then I could also say, well, I can take another reachable, 20 plus 2 in a sense, but of course 20 is less than 20 plus 2, and so I would stick to that value basically. And so you can show, and you can easily see in a sense, that by replacing this plus by a minimum over these variables, over the p here, that I will actually compute the shortest path, basically. After computing, what I will get is that for all the nodes in the graph, I will basically know what is the length of the shortest path in these nodes. So reachable of A will have value 0, right? Because that's here. Reachable of D will have value 20. Reachable of B will have value 20 plus 6, and so on, basically. And so you'll get simply by playing around with these semi-rings, you'll get like the values. You can do that also with probabilistic stuff, like probabilistic graphs, like here. You can take the most likely path in here, by just replacing plus by max and product by product. And if you're working with these probabilistic edges, like we've seen in Biomine, like we've seen in Problog, you'll get the most likely pass over here. And then there is, what Prism does, and also what Dyna does, is they basically replace plus by plus, and they work with these probabilities on facts, because that is what you do here. These edges are nothing else than probabilistic facts. And if you use plus and multiply on this, will you get the right probabilities, or will you get something different? Anybody trying to wake you up, just before the lunch break? Will this work? So what does it do now? If I sum here over multiple passes, every pass corresponding to a proof, if I do that, well, I'm actually counting on the fact, if I use a probabilistic semi-ring, I'm counting on the fact that all the proofs, all the passes are disjoint. And in generally, they are not, right? We've seen that this is the basic problem for Problog. It's the basic problem for Bayesian networks, that you have to be very careful with summing like this. And both Dyna and Prism are actually making this assumption that you can sum up these things, so that every proof that you find is non-overlapping, is disjoint from the others. And that means that if you apply that to this kind of graphs, you can get probabilities of 5, 7, or 100. So you don't get probabilities anymore. And that's why these are, in a sense, much, much faster, right? You don't have to cope with this problem. So the problem is a lot easier. On the other hand, it's a lot more restricted. You don't get the things you really want to get. And that's something to keep in mind. Still, in a lot of cases, when it applies, it's lightning fast compared to Problog. I mean, Prism is like lightning fast, but it's clear why it is the case. it makes this assumption that simplifies things a lot. And I think by now, probably Daisuke Sata also has a version that might work with, but I haven't checked on the latest. He's also into other stuff these days. After 25 years of Prism, it's a really, really cool system that I would like to recommend. It's a little bit more Prolog-like, but still. So what we've done is build a version, of course, that is working with semi-rings, but doesn't suffer from this problem. And the idea is that you've got Problog, and very much like on the example that we had before, you label, you use labels on the facts. These labels can come from commutative semi-rings, and you can use a lot of these semi-rings there, and inference is based on Problog principles. And then you can actually look at two key properties. One is, does the disjoint sum property hold, yes or no? If it holds, well, you can simplify inference. That is what Prism, that is what Dyna does. If it doesn't hold, you have to go for the knowledge compilation and all of that, basically. That is like the first dimension. And yeah, you can show that the disjoint sum property, it basically holds, like in the case that you're working with an OR, like true or, well, if you take any fact, no matter what the value is, what the label is that is associated to that, if you take simply an OR of these two facts, that's equivalent to that, the label of that fact, basically, right? And so that is the disjoint sum property will hold if that is the case. And then there is the other property, which we've encountered when we were looking at the difference between weighted model counting and number sets. In weighted model counting, you could get arbitrary weights to your literals, and so you could get a weighted model count of 750. If you're working with the probabilistic stuff, so that the sum of the label of the true fact and the sum of the label of the false fact, well, that always needs to be equal to 1, right? That's why you get probabilities. And so in that case, you can also make certain simplifications that hold. And the Problog case, let me show that first. The Problog case is basically here. The disjoint sum property does not hold, but the neutral sum property, the fact that the label of P plus the label of not P is equal to 1, that holds, and then you're kind of in the Problog inference that we've seen. The weighted model counting, the thing that we needed to do there, or even the model counting, is that, and we've done that, if you would compile your formula, and we've seen that also in the DPL algorithm, I couldn't just say, well, I get a 1 or a 0, I needed to do this kind of multiplications, right? I needed, in some of the leaves, I needed to look at, okay, I've got two variables below, so I got 2 to the power 2 of the possible counts that I have, and so I need to get these guys involved. Here from A, I know that whenever A is false, I would get into this branch, but you need to take into account like the other variables here, and you need to do a process that is called smoothing to take into account this kind of weighting. So that's even a bit more complicated. Now, why am I telling you all this? I'm telling you all this because, well, these things are pretty powerful. You can compute with these logics, yeah, the probabilities like we've seen. You can compute shortest passes, you can compute like MPE, but you can also do like a lot of other semi-rings. You can even build BDDs as you are going by associating to as labels to your nodes simple BDDs and then composing these BDDs as you go. So it's really a very powerful mechanism. And if you remember one thing from this lecture, in addition to maybe all the cool Problog stuff, then I would say semi-rings, keep that in mind. They're pretty powerful. The interesting one is over here. you can compute gradients with the Simulinks. And this is what we're going to use next in the deep problem. It's actually a very, very simple extension of Problog. And again, we've looked at what, remember that when I started, I said, look at the simplest, non-trivial thing to do, right? We were trying to unify logic and probability theory. So I took propositions and random variables and said, let's make them the same, right? Now I'm trying to mix logic with neural networks. I'm going to do the same. I'm going to look at the simplest non-trivial thing. What is the simplest non-trivial thing that I can see about a neural network? Well, just consider it a predicate. Just consider it like a proposition. And this is the basis of deep problem. I should say this is very new work. It hasn't been published except on arXiv. And it's work especially by Robin and Sebastian and Thomas and Angelica, who have been involved in that. And the idea is really here, going back to this type 1, type 2 thing, or this low level and high level reasoning. There's so much to do about deep learning, and there's so much progress that has been made here. And I think also there is an interest in combining this progress of the lower levels with the progress that has been made maybe more gradually and less disruptively in the past 10 years on logics and starry eye and probabilities. And you basically want to combine the best of both worlds. There actually are appearing challenges from DeepMind and others that are really looking into this kind of niche. Later this week, you also get an excellent talk by Sebastian Riedel, who's like the authority in this topic, and who has been doing also things along the lines of deep Problog, but in a different way, coming from more the neural network perspective. We come from the logic perspective. And things they have been interested in is like looking at scenes like this, automatically generated scenes. And you see that it's very much like a kind of blocks world, but rather than having the representation of the blocks world, you just have the vision, you have just the image of this, this kind of scene. And the question is still, can you answer something like, are there an equal number of large things in metal spheres? So in order to answer that question, you need to be able to recognize a lot of the things. This is not yet what we can do with Problog, but what is common is that we're trying to mix it with, Problog with very, very simple images for now. And the key distinguishing factor, I think, with regard to a lot of the other approaches to using logic and neural network, is that most people have started from the neural network side and then injected the logic into the neural networks in order to make it kind of fully differentiable, to propagate the gradients, and they get often they have to make compromises on the logical side. What we've done is, what I said is the simplest non-trivial thing. You take a neural network and you consider it as a predicate. I mean, that's like really, again, the simplest non-trivial thing you can do. And then, okay, calculating the gradient. I just showed how we can calculate the gradient with these algebraic techniques. I just need to use a Problog and, yeah, change the computation, I mean, use the computation of the gradient, and everything should work as it does. And so that is the basis of deep Problog. The idea is that these neural predicates encapsulate neural networks. They represent facts of which the probabilities are determined by our neural network. And of course, you can then also train the things starting from the logical facts, and you can propagate them down to the neural networks. Maybe it's easier to show a little example. It's still very toyish, but I think it shows the underlying principles. I mean, so far, I guess with standard logical techniques, or probabilistic logical techniques, it would be impossible to process examples like this. where you've got an image of a 3, an image of a 5, and you would say the sum is 8, right? With traditional logic systems, this would not be possible. With, well, convolutional neural networks, you could easily do that. You would probably need a lot of training examples, but yeah, you could get like 18 or 19 classes here, and you could, if you train it with a lot of these images, you would probably get the right thing. However, if you have knowledge, and I guess that's the idea of this type 2 thing, if you have knowledge, also if you have, it's also the idea of high-level reasoning. If you have knowledge, maybe you can use that, maybe you can apply that. And this is what we do. What we do is we basically will write down little prolog, problog, deproblog programs which encapsulate these neural networks, and we'll then try to learn them. I mean, we do know addition, right? The task here, I mean, if you do know addition, the task is a lot easier, because then you only need to map the image to the label of the image, and to the number that is represented by the image, and you can do the kind of inference that you want to do. So for addition, the program that we write down is we add an image of a number plus an image of a number, and that gives a sum, which is a real number. And in order to do that, well, we take this neural predicate that will take my image and will output a number, the number that it represents. Here it's the same, and I just say the sum is equal to that, and that will be my result, basically. So here you see like an instantiation, right? Well, this digit represents 3, this digit represents 5, so that is like equal to 8. And the way that we incorporate that in our problog is simply like here. This is the kind of declarations that you need to make. Here is the representation. It's a pointer, in a sense, to your neural network. This is the annotation. I mean, look at the similarity with the annotated disjunctions, right? In annotated disjunctions, what we had is, remember the urns that we started with. We have color, and then we listed like a probability it would be green, it would be probability it would be blue, and so on, and the sum would be equal to 1. What we do here is we list all of the possible classes, right? We've got from 0 to 9. And then this neural network, what will we feed in here? We will feed in the first argument. We will feed in one of the images. We will feed in that. And what we want to get back is a probability distribution over these classes. So this is just a neural network in which you feed in an image of a number, and you'll get a probability distribution over the 10 classes. The general form is like that, basically, right? This is, again, your pointer to your neural network. You get the vector of inputs, and that can be anything. Can also be large, potentially. And this is like the outputs, the vector of the outputs. And then it's, okay, this is classified in this class or that. And okay, you can also condition it on something. I mean, we've seen in the case of the breaking of the glass that there were conditions under which certain effects would hold, under which these random variables would be valid. And that's very much the same thing that you can apply there. So as a kind of little proof of principle, what we did is we used this encoding, where you use these pairs of MNIST images together with their sum, and we train deproblog with that. And the way it works is simply by using the gradient similarity in problog, which will actually compute the gradient at the level of the digits of the neural network, and then from then on the neural network takes over, and you can propagate it downwards to the weights in the neural network. So it's like from the logic, you first do the logic, then down you go to the neural network, and so you train end to end, basically. It's differentiable end to end. And you can see here that we trained it and we compared it with the baseline convolutional neural network. And you see then that after a number of iterations, while deep problog gets a pretty good accuracy very fast, whereas the neural network also gets pretty good accuracy, but it requires a lot more data and a lot more iterations, and it never gets as good as deep problog. And in a sense, that's unsurprising, but it's also what you want to have, because you encode background knowledge, you give it more information, but it's also a way of coping with that information, which is shown here. So you get fewer iterations, you get higher accuracy. You can also, yeah? That's the loss function. So the loss function, the loss goes down, and you see that the loss for deep problog goes down faster than the loss for the neural network. The interesting thing is also that you can, once you've got that idea, you can do more complex things. So far, it was just about single digits that we wanted to add. Let's assume we're now adding real integers. Like, for instance, here we've got 35 and 82, which would be 170. Now, giving this training examples to the neural networks would be pretty problematic because the number of classes that you would get would be pretty high. What you need to do in Problog is very simple, and that illustrates also the power of the programming language. I mean, we do know how to do addition for multiple numbers. Well, you do know that you get like this simple program, right? If there's no numbers, then I have the result that I had before. That's the base case. And then if I have like a head and a tail, I take the first number, I multiply it, I multiply what I had already by 10. And, you know, I mean, this is just standard Prolog to compute addition, to compute this number if you would know the real numbers. The only difference is, again, this guy, which is our neural predicate, and it shows that also this works. Again, you can show that with multiple digits, it also achieves pretty good accuracy quite fast. We've done other things, comparing it to something that I'm sure you will be seeing later this week if Sebastian Riedel is talking. There is that connects also to program synthesis. In program synthesis, in inductive programming, also inductive logic programming, there is something called sketching. And what you do in sketching is you take a program and you leave out certain holes in there. And the idea is that given training data, you have to fill the holes. And this is also the kind of program induction that you can do with deep problog right now. It's the kind of program induction that some other systems do, like sketching. There is work by MIT that is really very cool on like getting program sketches for bit operations and all that. There's also related work, I think, by Steve Muggleton on like meta programming. MetaGoal is kind of going also slightly in that direction. But what you can do here is also put in a couple of holes in Prolog programs and then have it fill automatically by training it with deep Problog. And here you see like one such hole. This is just like bubble sort, right? And the only thing that you don't know is when a number is smaller than another one. Suppose you don't know that. There is no less than in your background theory. Then ultimately you would need to learn that. And what you could learn it from is like a couple of examples of an input of an unsorted list and then the sorted equivalent. And then ultimately you would want this whole to learn which number is smaller than which other number. And the way to do that is by filling in this hole. And you do know that when it's one case, when x and y are depending on this unknown relationship, which we know is less than, that you should reorder them. In the other case, if it's less than, you shouldn't reorder them, you just take that one. And so swap would be the kind of neural predicate here. And again, you can show that this works pretty well. It does work pretty well as compared also to the differentiable force, which is the idea of using holes in the force programming language, which is much, much, much more primitive. It's a very low level language, but it's kind of showing again that deep problem is able to do a little bit more than that. And we've also tested it on word algebra problems to compare with deep with differentiable force, basically. Maybe to conclude as part on the problem, let me say that deep problem is really merging three things. First, it's problem, and problem merges logic and probability. But then it's deep, so it's merging also with deep neural networks. And even though it's still very, very early days, one of the things we can do is like also bring back the probability into the game in a sense. And so we did also one experiment to show that, and that's like our favorite example for introducing problog, which is like you know, the urns and the coins. And the thing that we did there is rather than assuming that you know the value of the coin and you know the value of the color, that what if you would give it to a camera, right? So rather than knowing head or tail, suppose you show it an image. We've not done it with real images of coins, but we've done it with zeros and ones from the ANIS database. So 0 was like heads or tails, 1 was like yeah, the other thing. And also the colors were represented by RGB values, basically. And the nice thing is that if you're given a number of examples of this and you train, that you can actually train everything at the same time, basically. You can actually learn the probabilities of drawing colors from the urn. You can learn that, and you can also learn the probabilities of getting ahead. And you also learn how to interpret, like, is the 0 that we fed in, is that the head or is that the tail? And also you learn how to map the RGB values onto, well, red, green, and blue, basically. Which is kind of nice, showing that you really have the best of all these worlds. So the implementation is basically coupling the aproblog implementation with PyTorch. And yeah, it's doing end-to-end training. Of course, it's still very early days. There's a lot of things we cannot do. There's much more we cannot do. But well, as you see, I'm quite excited about the work and also about the direction. I think it will keep us busy for a while. And there's a number of people working on that. Yeah, I have some further parts. Should I continue, or I can say still something about lifted weighted model counting using slides of key. Christian, you didn't show this, I guess, which is kind of fun because it will activate you. You'll have to think. Yeah.
Do you think a big problem can be used to learn also the structure of rules?
Well, sketching, filling these holes is like, to some extent, learning a little bit of a structure. That is what we can do now. I don't know what, I think it's going to be very, very hard to do more than that. But right now, I don't know, really.
Thanks. About the
Yes?
So, what is the input?
The image?
One single 28 by 16.
I would have to look for the details. I mean, it's like one image, one of the standard images, yes.
Okay, but then in comparison is no different. One dimensional problem.
So yeah, you basically what you do is you give a pointer to that image, the problog, and that pointer will translate the input to the neural network.
Yeah, but it's not different if you know that it's a pair of images versus getting a single.
Yes, but that's not exploited here. In the well, it's exploited in the problog part, but not in the neural network part, because. So there's one neural network that will map the image onto the value. No? Yes, okay. All right, maybe I should still do the weighted model counting, the lifting. I mean, this will activate you. It will show some of the interesting work that's not by me, but by Guy van den Broek, one of my former students, and which is also interesting to the discussion you had yesterday with both Christian and also with Weizsäck. Let me just go to that part, really. I mean, you've seen that lifted inference is like the holy grail of this kind of endeavor. And yeah, you'll also see that what Markov logic does, what Problog does, what all of these statistical relational AI systems do, is in one way or another, they do model counting. And the key trouble is that, I mean, if you look at statements with, let me show, like this. Well, if you just ground out or you do things naively and you do model counting for n people, well, you'll have 4 to the n possibilities to consider. And so if n is 1,000,000, good luck, right? It won't work. And that's why people like David Poole, like Guy van den Broek, like Dan Sucho, all these very clever complexity guys have been looking at ways to do what you do in logic. In first order logic, if you do proving in Prolog, or if you're really proving in first order logic, well, you will never instantiate, you will never ground out unless you're forced to. You'll never do that because things blow up. And so the question, which is the holy grail, is basically, can you change weighted model counting? Can you change other inference techniques like belief propagation, like variable elimination that you heard about yesterday with Christian? Can you change that so that it doesn't have to ground out always? And if you can do that, maybe you can also adapt the techniques like this knowledge compilation techniques to cope with that. And I'm showing all the solutions. I want to make you think. Let me just illustrate how that works and what complicates here. I've also already shown that there will be some cases where it will never work efficiently, right? Because that was the Sharpie completeness. I've shown like in the middle in this, when I was referring to this Dan Suchu kind of result, that if you added this one condition on this the third literal in your, this third condition in your rule, that things were becoming intractable. But there are cases where you can do it. And let's go through these simple examples. Here is a logical sentence, and assume we're just trying to count how many models there are. This is just a clause, right? If Alice is stressed, then Alice will be smoked. It's just propositional, no first order. So how many models would there be here? Anybody that there's, this is easy, right? Well, we can list them. right? All possible assignments of 1 and 0, true and false, to Alice stressed and Alice smoked. And then we get the value over there. We see that in the only case that will not satisfy this is, okay, if Alice is stressed, if that's true, and Alice smokes is false, then it will not hold, right? This case. So I've got 3 possibilities for the model count. Now let's assume I've got this logical sentence, and now it's the first order one because there's variables appearing in there. And I've got my domain, which is just listing Alice. I know that's the only possible constant that I have. The number of possible models is going to be exactly the same, right? Because one way of doing that is you ground out everything and you start counting how many models there are. This is also, grounding means that for all elements in my domain, I take X and I substitute it by that element of the domain and I list all these formulas, right? If I do that, I get just one formula, which is the one that I had on top, and that's exactly the same. Now, if I have this, and I take n people, how many formulas, how many models would I still have? I already showed it, so people should remember. But yeah, 3 to the power of n, right? For every person, I can take 3 models, and every of these models I can with the others. So I've got n persons, so 3 to the power n is what I will be getting, basically. Okay, now I'm introducing one other one. I mean, it has very similar structure, right? We've got 2 predicates with 1 argument, and I've got also female in there. Female is a proposition. Anybody that wants to look at this? Well, the thing to consider is, okay, if female is true, I got a statement like that. So if for female true, I've got basically 3 to the power n models, right? And then if female is not true, I know the condition part of my implication is not satisfied, so any model will do. So in that case, I've got 3 to the power n plus 4 to the power n models, right? 3 to the power n is the case when female is true. 4 to the power n is the case when female is false, basically, right? Everybody following, more or less? Okay, let's make it a little bit harder now. Now what we do is we do add another variable to that kind of model, and then things are getting a little bit more tricky. Yeah, basically what you now see is that whenever I take, I instantiate, what is it, X here, I get a formula like the one on top here, right? And so for every of these, I'll get the formula like that, and there is n of these, so I can again multiply all possible things here, and I get this kind of quality. And you see it's getting harder already. This is still, I mean, this is one where we've got 2 variables for parent of and 2 variables in the head, the same ones. This is slightly different. There's 2 variables in the body, but only one of them occurs in the head. And that's a bit of a different case. The insight that you need to make here is that you first have to choose among the n people who's going to be smoking. And if you choose, say that there was 5 guys smoking, that will be the green part. They will be true, basically. And then you can look at the K part. And so if from K to K, so if there's friends, it's basically about the assignments for friends, basically, that you're looking at. So from K to K, I mean, if Alice smokes and Alice is a friend of Alice, then she will also smoke. That will definitely be true. So from K to K, it will be true. From n minus k, I mean, if things are false, if, say, I take Alice and she doesn't smoke, then I don't care about the rest. So that will also be okay. If k is true, say Alice smokes, but Alice is a friend of Bob and Alice is in the red part, then I'm in trouble. That is where I don't have a model here. And here, again, okay, if Alice doesn't smoke, but she's connected to Bob and Bob smokes, that's going to be fine. That's going to give me a model. And so what you see is that in total, there is, well, there's n people. So there is n squared kind of groundings of this. And there you see that it's just really exploding. This is just for two variables. And so you already get like 2 to the power n n squared kind of possible interpretations. And then the ones that are not a model, I mean, the only ones that are not a model are basically these guys, right? It's the ones for K mapping, so the ones that have smokes true, that map to a friend that is not true. And there you get like this kind of property. Things get more complicated because here I've assumed that I knew the K, but of course I can still, the K that are smoking, I can still choose these. So in order to choose these, I have to get this kind of models, right? There's K, there's this number of ways in which I can choose K people that smoke from these N. And then, okay, this is assuming I know K, but in general, you want to have some overall possibilities there. So this is like the possible number of models for this. This is the weighted model count for this kind of formula with n people. And so you see that things are getting pretty tricky here, which also shows why this is getting quite complicated. And this is what you can then you can solve this kind of problems with the aid of first order knowledge compilation. I've mentioned at the start that we had BDDs, DDNNFs, SDDs, and so what she and others have been looking at is ways of really lifting these propositional structures to cope with the first order ones and then get still efficient operations on them. And that's been a quest that's been continued for, yeah, I would say a couple of years now. And I think right now people have a really good understanding of what is possible. They also have some hardness problems that are hard to get around. And the quest is continuing. I guess people like Christian, they're all into this game in a sense. Okay, and this is what you can then use as well. Okay, let me conclude. I hope I've given you a good flavor of what probabilistic logics are about, what they can do. Some key lessons, I think, yeah, you combine probability logic. We're looking into neural networks. It's not the only way that you can do that. There's different ways, but they will come along in the next few days. So thanks.